Hello, today we'll be presenting our work feature noise distillation using group convolutions for efficient plant pest recognition. The authors are Konstantin Khabarlak, that's me, Ivan Loktionov, Grigory Dichenko. We are from Dnipro University of Technology. The relevance of the problem lies in the following. Firstly, early and accurate plant pest classification facilitates selection of preventive measures to stop pest spread and improves agricultural product yields. It is well known that convolutional neural networks have high accuracy, but small neural networks that can be inferred in low-power edge devices show lower classification accuracy. In many cases, we want to infer on mobile or edge devices because they can be deployed directly in the field and they can process the information quite fast. Neural network distillation is an effective way to improve small neural network accuracy. There are multiple distillation approaches, however, there is still some room for improvement. We have also trained multiple neural networks. Up above, you can see large neural network architectures like ResNet, DenseNet, EfficientNet V1 and V2, and ConvNext Large. And at the bottom, we can see mobile-friendly neural network, MobileNet V3, which is quite popular in the research field. And as you can see, it has several times less, even in order of magnitude, fewer parameters, and it's quite fast. And it's by 4%, it has 4% power accuracy than the large neural network. And in this work, we want to propose an approach that will reduce that 4% gap. So what do we propose? Group convolutions have been shown as an efficient way of reducing the overall number of parameters and floating point operations in the neural network architecture with negligible accuracy loss. In this work, we show that they can be efficiently used to perform feature distillation and propose a novel group convolution mapper layer. We show that this layer outperforms the feature mapping layer without group convolutions. The proposed layer consists of two group convolutions with a small number of inner convolutional channels. We show that adding feature distillation with the proposed layer to Lagit distillation outperforms both Lagit distillation and feature distillation approach without group convolutions. As a benchmark, we use recently proposed IP100 to fine-grained plant pest classification dataset that has a large number of pest categories and training image in the field. So let's take a look at the neural network distillation scheme in detail. Up on top, we have EfficientNet V2 large neural network. Why do we select this neural network? Because among large neural networks, it has the highest accuracy, as has been shown by our experiments a few slides back. And on the bottom, we use MobileNet V3 large. We have considered multiple neural networks, mobile-friendly neural networks here, like MobileNet V2, SqueezeNet, ShuffleNet. Typically, MobileNet V3 has better accuracy, yet still it is quite friendly for the modern mobile devices. Also in here you can see that we have multiple, we have the group convolution mapping layer. In here, it has two convolutions that have a small number of inner features in between. Why do we need group convolution mapping layer at all? Because feature maps of the large neural network and small neural network have different sizes, and to compute some kind of loss between them, we have to map those feature maps using some kind of a layer, and we use convolutions here. Using convolutions is more efficient than, for example, using a fully connected layer. it offers fewer parameters and better accuracy. And in here we have the first component of our loss, loss for group mapping layer. And we have conventional losses for targets loss, as shown in here, and soft targets loss. That's also a distillation loss. So let's take a look at those in detail. So the targets loss is loss between actual true labels. That is supervised loss between true labels and labels predicted by the neural network. We use cross entropy here. Soft targets loss was also based on distillation. In here, we have the loss as proposed by Jeffrey Hinton. We have temperature denoted by T, and we use supervision from a teacher network, large neural network, to train a student neural network. And also we add group mapping layer loss. That is also a distillation loss, where we compute an average loss for the mapping layer. We apply the mapping layer to the student features. And then we compute average mean squared error between mapped student features and teacher features. And we use these three loss functions to formulate final training loss. This is weighted loss that is weighted by coefficients gamma 1, which corresponds to the grouping mapping layer, and gamma 2. And we also weight the supervised targets loss using the same coefficients as is shown in here. And this is the final loss that is used during the training. So on the slide in here is computed the group mapping layer loss between features, and in here we have a loss between outputs of fully connected layers, both supervised loss with true targets and soft targets loss between teacher and student targets. As you can see, the proposed approach has several hyperparameters that can be further optimized to improve neural network, student neural network performance. As searching all of them in a single pass would have required more than 8 GPU days of training, we have split the hyperparameter search in 3 stages, with the first one that search inner channels between those two convolutions in the mapping layer, the number of groups in those layers, convolutional kernel sizes, regressor weight gamma 1, distillation weight gamma 2, and distillation temperature. So let's see the results. First, we have searched mapping layer inner channels and number of group convolutions. We have found that the best results are given by the following configurations. In all cases, we utilize several group convolutions. As we have found out, using group convolutions is important to improve the student performance. We have experimented with one group, which is a conventional convolution, and it has lower accuracy than with the proposed approach. Next, we use two best configurations. We use two of them because they have quite different number of parameters, and we are interested in performing research on both of them, which one will be better. On stage 2, we search mapping layer kernel sizes. Here we consistently see that using a kernel size of 3 for both mapping layer convolutions offers the best results. Next, we search loss weights gamma 1, gamma 2, and distillation temperature. In here, you can see that by searching these parameters, the configuration with the number of inner channels 64 and fewer parameters has now higher accuracy than the configuration with larger number of inner channels, which we use as the best configuration. Summing it all up, the best hyperparameters for the proposed approach found are shown in this table. We have also visualized several hyperparameters using heat maps. In here you can see the visualization of convolution 1 versus convolution 2 number of groups, with the best results shown with lighter colors in here and in here. On the left, we show for 64 groups, and on the right for 512 groups. In both cases, you can see that using one or too many groups will result in worse accuracy than if we use, for instance, 4 or 16 groups. We have also investigated which hyperparameters have the most importance for this model, and it turns out the highest influence on accuracy, on test set accuracy, is by convolution 1 groups followed by convolution 2 groups. We investigate on our plant pests, on the plant pest dataset that we have used. Per class accuracy, the dataset itself has more than 100 classes, so we sort accuracies of models and show every 10th class. As you can see, on average, the distilled MobileNet V2 has, as shown with green color, has intermediate place between large teacher shown in blue and non-distilled model in orange. However, in certain rare cases, for instance, for rice shell pest, the non-distilled model has better accuracy still than distilled, but on average, the proposed model is better. So let's take a look at certain classes where the model has improved or not. For instance, there is an illustration of army worm. Non-distilled model is wrong, with high confidence, by the way, and the distilled model improves the situation the same way in here and in here. There are certain cases where no improvement is observed. For instance, for this illustration, the correct class is Lavana imitata millicar, and both models are mistaken, and interestingly, they show different classes. So let's take a look whether those classes are similar in any way to this illustration. So this is the image of this class that no notch distillation model has been confused with. As you can see, it's quite similar, and this is the creature that our distilled model has confused these two illustrations. So as you can see, the dataset is all about quite a fine-grained classification. In conclusion, with its work, a novel group convolution-based feature mapping layer is proposed that significantly reduces the number of parameters in the mapping layer and improves the student neural network accuracy. As you can see, by utilizing the proposed notch distillation approach, MobileNet V3 neural network performance has been improved from 72.14% to 74.83% in the plant pest classification task, and the approach has also improved over vanilla notch distillation approach, as shown by soft targets plus targets. Future work will be focused on deploying the trained model on Raspberry Pi for stationary greenhouse plant pest monitoring system, and further improving accuracy of fine-grained plant pest recognition. So we are planning to solve detection and segmentation tasks at large distance. This research was carried out as a part of scientific project funded by the Ministry of Education and Science of Ukraine. Thank you for your attention.